Alright, so these electron configuration notes are going to cover all of the things that we did on pages 8 through 10 that were notes. And I've broken this up into multiple different sections and posted each of those videos separately, but this video covers everything on page 8, 9, and 10. So if you only need one part of these videos, one part of these notes, you might go watch one of the separate videos that are labeled with the topic and the page number. So here on page 8, we learned the basics of electron configuration. This is sometimes called complete configuration. This is the normal full configuration that labels every single electron in an atom, where it's at, what energy level, and what orbital shape it has. Now, as page 7 talked about, we have different shape orbitals, and each of those shaped orbitals corresponds to a different area of the periodic table. In the video where I kind of showed you the building of the atom, where all those different shaped orbitals got added in a certain order, well, we're going to add them in that specific order based on their location, the element's location in the periodic table. So there are 4 main blocks corresponding to those 4 main shapes. The S block, those spherical shaped orbitals, get added to the elements in the first 2 columns of the periodic table. Now it is a block, and this looks like a rectangle, even though if you look at your periodic table, it kind of has a little chunk out of that second column. It starts lower down. Well, that's because helium technically could and should fill in that second column of that periodic table. It's also an S block element. It's just over there at that far end of the periodic table for some other special reasons. Underneath helium is what we call the P block. Nice rectangle there, full of elements. The ditch of the element between the S and the P block is called the D block. And then down there, it looks like it's separate from the periodic table, is the F block. Now it's not really separate, and this is important here. Let me show you what the periodic table is supposed to look like real quick. This is what the true full periodic table looks like when it's all put together. We have our S block elements here, our P and our D, and then our F block are here between the S and the D block elements. And that bold line that you see at the bottom of your periodic table between the S and D, only in those bottom 2 rows, is supposed to kind of show you that that's where those F block elements get inserted. The only reason why they're separate is because this periodic table, in its true full form, is just so long and skinny. It doesn't fit very nicely on a piece of paper. So because we don't use these F block elements very much anyway, they take up a lot of space, then we pull them out, squish them to the bottom, and our S, D, and P all fit across a piece of paper a lot nicer. Now, something to write in your notes, something new, is that each of these areas has a different specific energy level that they start at. Each energy level basically can add a new shape of orbital. So our S elements, our S block elements start at 1 on energy level 1, P start at 2, D start at 3, and F start at 4. This is important because, as you see in your notes, you have a periodic table that already has a lot of labels in it and on it. And I want to help you understand where those come from, because your periodic table you use on tests and quizzes are not going to have those labels. So I'll give you a dry erase marker so you can add them, but you kind of have to understand what they are and where they belong to get there. So if you have a paper periodic table that you'd like to add these labels with me, I'd highly encourage you to do that. And I'll show me adding this with you in just a moment on a periodic table that looks just like yours. But when we say that S starts at 1, that means that the first row, top left block, or kind of row of the S block is called the 1S. P start at 2, so the top left square, the beginning of that P block, is what we call the 2p orbitals. D start at 3, so 3d there at the top left of our D block, and F start at 4, so 4f there, the top left of the F block. These are our starting points for all of these blocks. And as we go down each row, below the 1s is the 2s, then the 3s. We're technically going up in energy level, building up our atom into bigger and bigger spheres there as we go to higher and higher energy level, but they're all still spheres. Over there in the peanut shape, the p block, those peanut-shaped orbitals, 2p is the smallest p orbitals we have. Underneath it, we start adding a bigger and bigger, third energy level, fourth energy level. They're still peanut-shaped, but they're bigger and bigger as we build our atom. As you might expect, underneath 3D is 4D, then 5D, 6D, and underneath 4F is 5F. So I would definitely recommend that you write these on your periodic table. This is one of the most helpful things to writing our electron configurations. Just start with those key labels, 1s, 2p, 3d, and 4f. And just like I did in that image, underneath 1s, let's just make those numbers bigger every time we go down a row. So we got 2s, then 3s, 4s, all the way down to 7s. And I know we have these number labels here, but I really think that it helps to see these as part of those elements so we can go through our elements. We can add underneath 3D, 4D, 5D, and 6D. Underneath 4F is 5F. And all we've got to do is come over here and finish out our P's. We've got all of the same labels that you need, or that you have on that little bitty periodic table in your notes. But this is going to help us so much, because what we're about to be doing, and I'll go back to that packet in a second and fill out a little bit more notes and explain stuff to you. If I'm getting to a specific element, if I want to write the electron configuration for something like nitrogen, what we need to do to write its configuration is go row by row across the periodic table, labeling what orbitals we hit, so kind of what areas we're going through, and how many squares we go through in that type of orbital, in that area, and put together a configuration. And we just keep going till we get to our element. So nitrogen, we'll write this out again in a second together. We always start at the top left. We always have to start at 1s. And since we're going through not just one, but two squares here, it's going to be 1s2. After we get to the end of a row, we go back to the beginning of the next row, where we see 2s. And since there's two squares here for us to go through, that's 2s2. You might say, oh, but miss, there's more squares that I need to go through to get to n. But those are actually 2p's. So those are a separate term that we need to go through. And we don't just stop at that first square or the second one. We have to go 3 squares in to get to nitrogen. So nitrogen's configuration is 1s2, 2s2, 2p3. If I was going to try and get down to one of these elements in the 5th row, I'd have to finish out all of those p's, get to the end of the 2nd row, go through the entire 3rd row, go through the entire 5th row, and then the 4th row, then the 5th row until I get to my element, naming every single type of orbital that we hit along the way and how many squares of that type we go through before we get to the next type, before we get to our element. So these can get rather lengthy, but if you have a map like this, a periodic table with those labels on it, then you've just got to take it carefully and go row by row, labeling where you're at and how far you need to go in each. Now, this is kind of like giving directions on how to get to an element's house. We're just going row by row, saying where we hit, how far we go, like turn onto Miles Road, go 2 blocks north to get to Zaxby High School. But what you've got to remember is that all of these terms, just like what we wrote back on page 7, and this is already on page 7, you don't have to write this here on page 8. Each of those big numbers represents the energy level that those electrons are on. The letter represents the shape of the orbital the electrons are in, and the little bitty exponent number, that superscript, represents the number of electrons in that orbital. So helium, its configuration is 1s2, and what that means is that it has 2 electrons in a spherical shaped orbital on the first energy level. So it's important we don't lose that meaning as we work through this analogy of treating the periodic table like a map and giving directions to our element. Now, this little note is already written in your packet. The Aufbau principle tells us to fill from lowest to highest energy. Number of electrons is the number of squares. The Aufbau principle means that we have to start at the lowest energy. We always have to start at 1s, even though it's really basic, it's really simple, is extremely repetitive. We've got to start at that 1s orbital every single time. So let's do a couple of these configurations. I can't fit that whole periodic table on the screen while I'm still writing these configurations, so I'm just using that itty-bitty one like what you have at the top of your page, but since it doesn't have the element symbols there, I've gone ahead and highlighted those squares where our elements are. And these are some of the simplest, smallest elements. Hydrogen is H. It's right here at the beginning of our periodic table. And since that's where we start writing configurations, we just need to label that. That's 1s, and since it's in that first square there, that's going to be 1s1. To get to helium, which is that second square on the first row, that's still a 1s orbital, but since we have to go to the second square, we write 1s2. Note, we don't write 1s1, 1s2. We don't have to label every single square we pass through. Just like if I'm giving you directions, I don't have to say, turn onto Miles Road and go 1 block, and then go another block on Miles Road. If I need you to go 2 blocks, I'm just going to say, turn onto Miles Road and go 2 blocks. It's much simpler and more direct that way. So to get to lithium, we have to start at the beginning still. We always start at the beginning. But lithium is down there in the second row, but we still have to go through all of the first row before we can come down to the second row. So we start at 1s, and we still have to go through both of those squares before we're done with the first row. And then we can come across the second row, which is the 2s orbitals. Since lithium is the first square in that section, then it ends at 2s1. So 1s2, 2s1. We got 2 terms here because we got 2 different types of orbitals here. Beryllium is right next to it. It's 2 squares in to that 2s. But we still have to start the same place with 1s. Go 2 squares over in that 1s, and then we can go to the 2s row, and we go 2 squares over there, and that will get us to beryllium. So hopefully you can kind of see this progression where this number is just increasing by 1, or we're adding a new term and increasing that by 1. Now on this next set of elements, we're going to start jumping around a little bit more, but we started with those simple elements to help you see that progression. Now I've already written out nitrogen once for you, but I want you to practice this the same way that we did. Nitrogen's down there in that second row. We've got to go all the way across the first row first and through the beginning of that second row before we can get all the way over to nitrogen. So we're going to start at 1s and go through 2 squares. Gets us to the end of the first row. Then at the beginning of the second row, we hit those 2 s's. Even though we're going farther, we only have 2 of those 2s squares to go through, because after that, on our way to nitrogen, the rest of those elements, the rest of this square over here, are the 2 p's. So we've got our 2 p's that we're running into next, and in order to get to nitrogen's square, we want to go 3 squares in. Don't stop at boron or carbon. We have to go 3 squares in to get to nitrogen. For magnesium, which is down on the 3rd row, planning this out, I've got to go across the whole first row and the whole second row, and then we go a little bit farther to get to magnesium. So that whole first row is taken up by 1s2. That second row starts with 2s, go 2 squares in, and then we've got to remember we're still jumping over the 2 p's. We have to finish that second row before we can get to the 3rd row. And if we're trying to go through all of these p's, if you count them, there are 1, 2, 3, 4, 5, 6 blocks, 6 squares to go through here. And we got to go through all of them in order to get to the end of the second row. So 2p6. And after the second row, we're not quite there yet. Magnesium's on the 3rd row, so that's 3s to start with. And since it is 2 spaces in, that's 3s2. Iron is a little bit farther down. It's in that 4th row, which means we're going to have to go even farther. Finish the 3rd row, and then go a couple of spaces over in that 4th row. So I'm going to do those first 2 rows for you. This is getting pretty repetitive. 1s2, 2s2, 2p6. That's gotten us through the entire second row, first and second. Where do we go once we're done with the second row? To the third row. We do have to go 2 squares in to get through those 3 S's, but then we've got to keep going, finish out that third row with all 6 of those 3 P's. That gets us to the end of the third row. Where do we go next? Beginning of the fourth row. It's the 4 S's. There's only 2 4 S's there. They're right up against those D's, but those are completely different. So that's going to be 4S2. And then the next thing we hit are those 3 D's, and that's where iron is. It's 1, 2, 3, 4, 5, 6. 3, 4, 5. It's supposed to be 6 spaces in. Let me double check. Yes, it is. After counting on my periodic table where I can see those symbols, my little blue square was off by 1. But if we count that, that is 6 squares in. So that's 3D6. Now don't worry too much about the fact that this 3D came after the 4S. That's just the way the periodic table is put together. Remember, our S's start at 1, our P's start at 2, D's start at 3, and F's start at 4. It's weird, but we just keep going across row by row, labeling what we hit and how far we go, and just trust the chemistry that there's a reason for it. There's some quantum mechanics reasons we can talk about if you want to take AP Chem, but it's nothing you need to worry about in honors chem. Just follow the periodic table and those labels row by row till you get to your element. Now, gold is all the way down here, AU. So this is going to be kind of a long one, but we just need to go, even though that's down in the 6th row, we're going to take it row by row. 1st row, 2nd row, 3rd row, 4th row, 5th row, and then most of the way across the 6th row. What I want to remind you about now is that when we get down to the 6th row, between the 6S and the 5D, we have to go through that 4F. And it is only going to be the 4F because that 6th row only lines up with the 4F. We don't have to go through the 4F and the 5F. We just go through one row of each letter as we go across the periodic table. It's just that those F's line up with those bottom 2 rows of our S's and D's. So we've got to remember where that bold line is like all of those F's squeezed into that one bold line. So we've got to go through all of them, and there are 14 of them when we get down there. So we just can't forget about those specific elements. So just like before, I'm going to get you through those first 2 rows without having to kind of walk you through it. 1s2, 2s2, 2p6. After the end of that 2nd row, we go to the beginning of the 3rd row. Go 2 squares into those S's. Then we have to finish out that 3rd row. Go over to the 3 P's. Go through all 6 of them. Then our 4th row. Start it. Go through both of those 4S squares. Then down into the 3 D's. If we're going through all of them, because we need to finish this whole row, there are 10 squares there if we count them. We're still not done with that 4th row. We got to get through those 4 P's. There are 6 of them. Then down to that 5th row, 5S. Go 2 spaces. Then down into the 4 D's. Go through all 10 of them. Finish out the 5th row with the 5 P's, all 6 of them. We're almost there. 6th row starts with 6S. Go 2 spaces. And this is where we've got to remember that we need to go through our F's, or really just the 4F. And there are 14 of them if we're going through all of them. And then we can finish up in the 5 D's. And in order to get to gold, we're not going through all 10 of them. We have to go through 9, stopping at the 2nd to last space. So I know it's a long configuration, and I barely managed to make it fit on my line. I hope that you fit it all in on that page. But it's just a systematic process of going through row by row until we get to the element square that we've got. Now, I know I say optional, complete ND's configuration. Really, it's going to be basically the same as gold's until we get through that kind of 6th energy level there, because ND is down here in the F's, and a lot of people think that that's even harder because it's the F block, but we already went through the F's. So if we wanted to stop in the F's, we'd have to go 6S2, but then we just go 4F, 1, 2, 3, 4, and then we're there. It's actually shorter than gold because we didn't have to go through all of the F's and then the D's. So don't let the F's freak you out. They are a little weird and different, but they're not that freaky. Now, the practice problems that go along with this are page 11 and 12, part A. That's what we call the complete electron configuration. It starts at 1s and completely labels every electron in every orbital. I'm going to teach you about B and C next. You can also do a little bit of page 13, where it's starting to have you use a configuration to find an element. You can also start looking at some of these configurations and fixing some of the issues. 3 out of the 4 of these have issues, and you can only really look at this first one for now, but I'll remind you of that later once we can finish these out. This is just like what we wrote at the bottom of page 7. What do each of these parts of our configuration mean? It's not really the area of the periodic table. It's not really the number of squares. It's telling us something about the atom. So go back, check page 7 if you need that there. Then 13 and 14 might be a little bit of a stretch if you're just starting this. You can come back to this later. But what happens with 13 and 14 is you're starting to do some analysis on some of these configurations. So even though it doesn't say write out the configuration for these elements, that's really what you're going to need to do so you can look at it and analyze it. So let me give you 2 examples here. In 13, we're asking you how many electrons are in p orbitals for the following elements. Well, you need to write out the configuration for these elements. Here I've done chlorine for you. And then you need to look at which terms have p's in them. And remember that the exponent number on those p's and every letter tells us the number of electrons in those orbitals. So here, because I have some 2p electrons and 3p electrons, if we add those together, that tells us that chlorine has 11 total electrons in different, various energy levels of these peanut-shaped orbitals. We do the same thing when it's asking about our 4th energy level electrons. It's just that the energy level is the big number before the letter. So we look for all of the terms that have 4s in them, and then we add up the electrons in those orbitals. This is 2 plus 1. It means that gallium has 3 4th energy level electrons. So use your configuration as a guide. Write those out if you have the space on the paper, or write them out on a separate sheet of paper, and look for the p's or the 4s in order to add up the total number of electrons. We can do the rest of these problems in page 14 stuff once we learn some more configurations. So the next type of electron configuration that we're going to be working on is called orbital notation. And you should write down this blue stuff here where it says orbital notation. The way this is different and special is that we're actually going to draw out our electrons in their orbitals. But we're not going to try and draw out those funny shapes that the orbitals are. We're just going to draw our electrons as arrows and our orbitals as simple lines. So we're going to be putting lots of lines, arrows on lines. Now, what you see below with all of these lines is the longest possible orbital notation. And that's not there for you to fill in, and I'm never going to ask you to draw one that is quite this big, but I want you to be able to see this pattern. All of these different orbitals have a different number of lines, or rather, each different letter, each different shape orbital has a characteristic number of lines. If you look through here, no matter whether it is a 1s, 2s, 3s, or even all the way down here in the 7s's, all of our s orbitals have one line with them. Everywhere that we see our p orbitals, once again, it doesn't matter the energy level, no matter whether it's a 2p or a 7p, they always have 3 lines. D orbitals all have 5 lines, and the few f's that we've got have 7 lines. Now this corresponds to the different orientations of each type of orbital on each energy level. If you remember back on page 7, I showed you how we had 3 different orientations of these peanut-shaped orbitals. On each energy level, we have one along the x-axis, the y-axis, and the z-axis, and they all kind of combine and overlap into that electron cloud around the atom. But there are 3 different p orbitals there, and we're just representing each of them as their own simple line. Now, you are eventually going to have to draw your own lines, which is why you have to write down this part here. The first two examples, I've drawn the lines and labeled them for you. We're just going to practice drawing the arrows in, but then we're going to practice putting the lines down, and our electron configuration is a guide. So if you haven't watched your page 8 notes yet, that is essential to being able to understand what we're doing here, because we're using those configurations as a guide to tell us what to do with these orbital notations. Now, technically back at the bottom of page 8, there are some rules for how to add our arrows to lines. And these are some pretty simple rules. There's nothing that I really think that you need to add to these rules. I just want to point them out to you so you can just look at them on my screen instead of flipping back. The first rule is Hund's rule. You want to maximize unpaired electrons, which is just a fancy way of saying the electrons don't want to be together if there's open spaces. Just like you wouldn't want to share a bed or like a seat with your sibling at home if there was an open seat or an open bed available. So in this example, if I had some configuration that had D4 in it, our D orbitals get 5 lines. If I only have 4 electrons to put on those lines, then they can each have their own line. There's no need to double them up and have them share lines when there are open lines available. Now, there are going to be times when we do have to double them up, when there won't be enough lines for every arrow to have their own. And when we do that, we need to make sure that they have the opposite spin, which basically means for our arrows, they need to go opposite directions. We can't have 2 arrows going the same direction on the same line. So, let's go fill in some arrows. Like I said, we're going to use our electron configuration as a guide. So I'm going to write oxygen's electron configuration here in order to help us see what we need to do. And because all we really care about is filling in our arrows here, the arrows represent electrons. Remember that these exponents represent the number of electrons in each of these orbitals. So that tells us how many arrows to put on these lines. When that says 1s2, that means we need to put 2 arrows on our 1s line. And if they're sharing the line, they need to go opposite directions. Now, you'll notice I kind of do some weird looking arrows. They're kind of half arrows, because if I start doing double-sided arrows, these start to run together. You might be able to tell I'm already messy enough. I don't need to make anything any messier. These have to have direction. They can't just be lines. They have to have some direction to them. So you need some of those arrowheads there. If you can write these small enough and neat enough, make them fit, but that takes up too much time, and I am not that neat. So it is up to you how you want to draw your arrows. It doesn't really matter. As long as they have a line and a head on them to give them a direction, I'm fine with that. So 1s2 got 2 lines. This 2s2 term means the 2s line gets 2 arrows. And then the 2p lines are going to get 4 arrows. And that would mean 1 on each line before we double up. You might already be able to realize, 4 arrows, 3 lines, 2 of them are going to have to share. I won't be looking over your shoulder during the test to see what order you write them in. So if you want to start with them doubled up and then single, that's fine. But it's an easy habit to get into. If you start with them doubled up, you might write your 2p4 like this, and that is incorrect. These last 2 electrons do not want to share a space if there is an open space available. So it is important that we end up looking like this. And we do generally fill from left to right. So that doubled up set of arrows should be at the far left. It shouldn't be at the far right or in the middle. So as you saw me do at the first kind of step, I always draw mine in left to right, singly first, and then I double up. It's just a good habit to get into, so I never accidentally double up where I shouldn't or have them going in the wrong order. Now, chromium is a bit longer, so let me write out that configuration. But once we have this configuration, we can use that as a guide to fill in what we need to here. Just like before, 1s2 means we put 2 arrows on this line. 2s2, 2 arrows on our 2s line. 2p6 means all 3 of these are going to be full with our doubled up arrows there. 3s2, this is going to be full and doubled up. 3p6, this is full with doubled up arrows. 6 arrows for our 3 lines. Again, trying to make sure I have clear direction on my arrows. 4s2, and then finally 3d4. Just need to make sure that I have my 4 arrows going in those 4 separate spots. Don't let this empty orbital throw you off. We still need that 5th line there. If we were drawing this out, we'd still need to draw it. It's just empty. That empty orbital tells a chemist something about the reactivity of this element. It's either going to be real aggressive about getting 1 electron or about giving up some of these electrons that, don't have it completely full or even completely empty. So there's some reactivity stuff that we know when we see a configuration like this. So we have to leave those empty spaces in order to be able to see that and understand that. So let's do some examples where you have to draw the lines. Sulfur's configuration is 1s2, 2s2, 2p4. I take that back. It's 1s2, 2s2, 2p6, 3s2, 3p4. My bad. And so if we use this as a guide, when we see 1s2, we need to draw our lines, and S's only get 1 line. You've got to remember to label it as 1s, and then that exponent 2 means we put 2 arrows on it. Going to the next term, 2s2. S's still get 1 line. They always do. We just label it as 2s, and then we put 2 arrows on it. 2p6. P's get 3 lines. All of them share that 2p label, and then we're filling them all with doubled up electrons because we need 6 electrons on those 3 lines. Then 3s2, S's get 1 line. That gets 2 arrows because of the exponent. And then 3p4. 3p means 3 lines. 4 arrows means just like oxygen, we're going to have doubled up arrows on that first blank and then up arrows on the next 2. And just like oxygen, sorry about that, because these have some very similar ending arrows here, some very similar configurations there on the outermost layer, they're going to have some very similar reactivities. Now for these last 2 elements, I did not do them in class, and I am not going to draw their orbital notation for you here, but I am going to make sure that you have what you need in order to write out that configuration on your own. So I'm going to give you the normal full configuration for them, and then I just need you to turn this into their orbital notation. It's 2, 2p6, 3s2, 3p5. So use this as a guide, draw all your lines, make sure to label them, and put all of the arrows where they belong. And then, once you're done with those, you can start looking at pages 11 and 12. Part B on pages 11 and 12 is this orbital notation stuff. Hopefully you already have the complete configuration there, so you can use that as a guide as you're creating your orbital notation. And there are just a couple of problems on page 13 that are orbital notation. So in the top, you're using that to identify an element, and then in question 10, you're identifying if that's correct or incorrect there. Okay, so on page 10, we have some of our final configurations, and the first one is what we call noble gas configuration. And on the periodic table, the noble gases are at the end of each row. So they're here all the way from helium down to OG. These are the noble gases, and we're going to treat these kind of like landmarks, so we don't always have to start all the way back at 1s2. The way we're going to do that is by putting the noble gases symbol in some of these square brackets, and then we're going to use that as our starting point to finish out the configuration. So we don't have to start all the way back at the beginning, but there is always just one noble gas that we can or should start at in order to get to a specific element. And that's going to be based off of where the element is in the periodic table. For example, we're going to be starting with magnesium and gold as these first two examples. On our way to magnesium, we went across the first row, past helium, and across the second row, past neon, and then a little bit farther. So neon is going to be our starting point for magnesium. It's the last noble gas we pass through on the way to neon. It's the last noble gas we pass through on the way to magnesium. Now, instead of trying to trace this row by row by row, the easy way, no matter what, once you find the element you're trying to get to figure out what noble gas you need to use as your starting point, go to the row above it at the end. That's always going to be the last noble gas that you pass through on the way to your specific element. So for gold, we're going to be starting at xenon. So for our magnesium noble gas configuration, like we said, we're going to start at neon because that was the last noble gas we passed through on the way to magnesium. Neon's at the end of the second row. Where do we go once we're at the end of the second row? Well, the beginning of the third row. That's where our 3s orbitals are added. And how many spaces in do we have to go to get to magnesium? 2. That is the that's the noble gas configuration. That is the whole configuration we have to write for the noble gas configuration for magnesium. Now gold, if you remember on page 8, gold almost made you want to quit. Your hand was falling off by the time we were finished with it because it was all the way down in that 6th row. But when we start at xenon, that last noble gas that we pass through on the way to gold, that's at the end of the 5th row. So all we've got to do to get to gold, start the 6th row. Go to that 6s, 2 spaces in. Don't forget that that bold line tells us we have to go through the 4 Fs before we can get to the 5 Ds. And there are 14 of those 4 Fs there. And then 5D, just 9 spaces in. And that's not that bad. That's all we got. That is gold's noble gas configuration. What that's telling us is we have the same electrons as xenon and then a few more. And honestly, these outermost electrons are the most important ones. So that repetitive 1s2, 2s2, 2p6 stuff isn't really the most useful way to spend our time if we're focused on those outermost elements, electrons. So there are 4 more examples, and I'm actually going to ask you to do these yourself. But what I want to make sure that we agree on is where we should start at for each of these. Where is the noble gas that we should start at? So I want you to look at your periodic table. Find each of these elements. Sulfur is element number 16. It's over there in the P block. Find sulfur, go 1 row up and to the end. And hopefully you agree, neon is the last noble gas that we pass through on the way to sulfur. So that should be our starting point. Fe is element 26. It's kind of there at the top middle of our D block. Find iron. There's a blank space above it, but just go 1 row up all the way over to the end, and you should be finding argon as the noble gas that we can start at. Borium would be cruel and unusual punishment to ask you to write out the full configuration for. It's all the way down there in the 7th row, kind of in the middle of the D block there. But with the noble gas configuration, if we find borium, element 107, go a row up to the end. Radon is going to be our new starting point, and that's going to make this a lot easier. And then xenon. Xenon is a noble gas. It's element 54, all the way over there in our last column. And a lot of people are tempted, well, it's a noble gas, so couldn't its noble gas configuration just be Xe? But unfortunately, no, it's not that easy. With our analogy about directions, that'd be like me asking you, hey, how do I get to Xenon's house? And you reply, oh, you go to Xenon's house. That is not descriptive at all. That is not helping anyone. Now, we know this isn't really directions, but we still have to do the same thing we do with every other element. Find xenon, and then go to the row above it. The last noble gas we pass through on our way to xenon is krypton, Kr. So these are your starting points. You still need to finish the rest of these configurations, and each of them is going to have 2 or 3 terms that you have to go through in order to actually finish this out. But none of them are going to be longer than 3 terms to get across the rest of that next row. So please feel free to check these with me in class. Make sure that you're on track, And then there's some noble gas stuff. That's the part C on pages 11 and 12. So hopefully you have A and B done, and this is a nice short way to finish that off. You have a couple of noble gas configurations on page 13, both to find an element with and to identify if you're doing that right or wrong. This should let you finish out all of question number 10 here. So remember, 3 of these are incorrect. You should only have 1 of them that's correct and 2 of them that are incorrect. Sorry, 3 incorrect, 1 correct. And then there are some noble gas configurations for you to do on page 14. None of that should take very long because these are so nice and short and simple. Okay, here in the middle of page 10, we have another configuration to write that's actually even shorter than noble gas configuration. Please make sure you write down this blue stuff. I would recommend you also write down the red stuff because it'll really help your future self and maybe even your current self remember what we're talking about here. Now, valence electrons. You've probably heard this word before, but it's probably been a minute. These are the outermost electrons in an atom, the highest energy level of electrons. And if you remember, these configurations, as much as we talk about them like they're directions, they're not directions. Elements don't have houses. They don't live on the periodic table. This is just an analogy that helps us understand what we're doing here. But when we write out terms like 4s2, that big 4 in front of the letter, or whatever the number is in front of the letter, represents the energy level that the electrons are on. So our valence electron configuration is only going to include the terms that are on the highest energy level, which means we're going to be looking for the biggest of those big numbers in front of the letters and only including whichever terms are in that highest energy level in our configuration. Now, the easiest way to find those highest energy level electrons is to look at the full configuration and just look for those biggest numbers. So I've written these out here for you. I'm not sure if you have space in your packet to write out the long way and the short way, but if you do, it might not be a bad idea. Because all we're doing is looking at these coefficients, the numbers in front of the letters, and asking ourselves, well, what is the highest energy level? What is the largest number in front of the letters in aluminum? And for aluminum, the highest energy level is the third. And we actually have 2 terms here who both have some third energy level electrons, the 3s2 and 3p1 terms. So both of those are going to be in our valence electron configuration. And that's all that we got to keep. No noble gas, no extra stuff, just 3s2, 3p1. For beryllium, the highest energy level that we get to is the second energy level. And there's only 1 term there in that second energy level, so that's all that we bring down, 2s2. That's it. I did shorten down tin and iron into their noble gas configuration here, just because they're a little bit long, and the great thing is, the noble gas configuration, while it makes it short, will always include the terms that have our valence electrons. So it's always a good option if we're trying to look for this valence configuration. And if you notice in tin, we have the 5th energy level is our highest energy level. We drop down into the 4th energy level a little bit in between, but we do have 2 terms here that are both in the 5th energy level. So we bring both of those terms and only those terms down into our valence configuration for tin. With iron, our highest energy level we get to is the 4th, and so we bring that 4s2 down, and that's it. Now, if I had told you that, oh, I have an element with some configuration 4s2, you might think that I left off some of the beginning part, but you probably didn't think I could leave off some of the end part. And if I said, oh, something's at 4s2, you might think I'm talking about calcium, but I'm not. This is iron's valence configuration, but it is exactly the same as calcium's valence configuration. For that matter, scandium through zinc would also, that first row of the D block, would also have a valence configuration of 4s2. So these are not unique to different elements. In fact, this helps us see some of the similarities between different elements. And if they have the same valence configuration, some of them are going to act and react in a very similar way. So this is not something we can use to identify an element, because once again, it's not unique, but it can help us understand some of the chemistry of our elements. Now, we don't have a ton of practice. Oh, that was just a big long example to show you that process. But we don't have a ton of practice with these, but there on page 14, question number 18, you have some valence configurations that you can write. So our final type of electron configuration is at the bottom of page 10, and these are called Lewis electron dot diagrams, or structures. Write down the blue stuff. These structures, or these diagrams, use dots to represent the valence electrons. We just talked about valence electrons in our valence configuration. If you haven't watched that part yet, please go fill that part in first. Because once we know how many valence electrons we have, and we can do that from that configuration, we can put that many dots around our element's symbol. And it is important that they go on this kind of invisible box around the element symbol. So if I have an element X, imagine this box around that element symbol in a nice square. And we're going to be putting our dots on the sides of that, not just in the corners, not lining everything, but kind of squarely in the middle of each side. And we're going to put one dot on each side of that element symbol before we start doubling up. And 2 dots is the most that we can put on any side. So a maximum of 8. Now, we're not going to actually draw this box, but you kind of need to visualize that around your element symbol as you're drawing the dots. Now, I'm going to write out the configuration for each of these elements so that you can understand where these come from. And we're going to derive how many valence electrons each one has. I promise you don't have to do this every single time, but you always can. The valence configuration will always tell us the number of valence electrons. So this is lithium's configuration, 1s2, 2s1. And the second energy level is our highest energy level. That's our valence electrons. And that 1 there tells us that it has 1 valence electron, which means lithium symbol gets 1 dot. It doesn't matter where that dot goes, as long as it's on one of those sides, or on top or on bottom, as long as it is along the sides of that lithium box, that invisible box. Beryllium is right next to it. It's at 1s2, 2s2. So the second energy level is still our highest energy level, except beryllium has 2 electrons in it, which means it gets 2 dots. It's important that they're on different sides. Doesn't matter whether it's top and bottom, left and right, left and top. Doesn't matter where they're at all. I've been doing this a while. I usually start at the top, work my way around clockwise. I'm not even 100% sure why, but it doesn't matter as long as they're on separate sides. Boron is right after beryllium. It goes all the way to 2p1. Don't make that think that you have 1 valence electron, because both of these terms are still in the second energy level. So we have 2 plus 1 is 3 total valence electrons. So boron gets 3 dots. Carbon is right after it, 1s2, 2s2, 2p2, which means it has 2 plus 2, 4 valence electrons. You might be starting to notice that as we go across, each square adds 1 electron to the atom, adds 1 number up in that top exponent area, which adds 1 valence electron. So you're probably not surprised to hear that nitrogen is going to have 5 valence electrons. Well, it ends at 2p3. So that 2 plus the 3 does give us 5. So we're going to put 5 dots around nitrogen, making sure 2 of them get doubled up on one side, but then the other 3 dots are on their own separate sides. I always put 1 on each before I double up, like with the arrows on our orbital notation. If you know there's going to be 5 dots and only 4 sides, you might know, okay, 2 of them are going to be sharing a side. 2 of them are going to be doubled up. That is a dangerous habit to get into, because once you start doubling, it's so easy to double up 2 sides to get 5. And that will not earn you full credit. You got the right number of dots, but they have to spread out if there is an open side available. Oxygen is going to get 6 dots. It goes all the way to 2p4. 2 plus 4 is 6 valence electrons, gives it 6 dots, which does mean that 2 sides are going to end up with 2 pairs. 2 of those sides are going to have some single lonely electrons on them. Fluorine goes all the way to 2p5, so 2 plus 5 is 7 valence electrons. So we're going to have 3 sides with pairs of dots, one side with a little lonely electron, and then you guessed it, neon is at 1s2, 2s2, 2p6, which means 2 plus 6 is 8 valence electrons, so all 4 sides have our doubled up dots. Now, I want to mention that argon, right underneath neon, has a very similar configuration. It is a little bit longer, but it ends at 3p6. So keep in mind, the third energy level in argon is its valence level. That's where its valence electrons are. But if we look at those numbers, the 2 plus the 6 is still there. So argon still has 8 valence electrons. So our number of valence electrons is the same in each column of the periodic table. We don't have to write out the full configuration and count up those numbers just to find the number of valence electrons. If it's not asking for a configuration, we can just use the periodic table like a guide. So I am going to ask you to draw out these 3 Lewis dot diagrams. It is important that you use their symbols. It's a silly point to lose. It would only be 1 point. But you can't just put dots around the names. That's not the way that we do Lewis dot diagrams. It has to be around the symbols. But let's go look at our periodic table at some of these patterns so we don't have to write out all those configurations to figure out how many dots to draw. So we saw that lithium has 1 valence electron. In fact, all of the elements in that first column have 1 valence electron. And you can probably see at the top of that column, it's labeled as column 1. So that 1 can kind of remind you, 1 valence electron. Same for column 2. They've got 2's above the column, 2 valence electrons for every element in that column. Now, our D block elements are a little weird. Technically, they still have 2. Everything has 2. At least that's the normal rule. Those D block elements don't always follow that rule until we get to boron's column. And boron, as we saw, has 3 valence electrons. Not 13, but 3. So if you focus on these A labels underneath the column numbers, because there are 10 columns of D's there, those A labels are kind of the main group elements, not with the transition metals, that the D block elements that don't follow the rules very much. The A labels will tell you how many valence electrons they have there. So if we're looking at our calcium and selenium and krypton, all we have to do is look at the numbers at the top of each of those columns. That tells us how many dots to put around those symbols. So that should be pretty quick and easy for you to finish up. And then there are a couple of practice problems later on that use Lewis dot diagrams. They're only on pages 13 and 14. We're done with 11 and 12 by now, hopefully. So it's really mostly page 14. I give you some diagrams for you to find the element, and I ask you to draw some diagrams on 17. Page 13, number 12, might not look like Lewis dot diagram problems, but this is the best place to figure out how many unpaired electrons are in each of these atoms below. If we draw nitrogen's Lewis dot diagram again, I know we just drew it, but it had 5 dots. 3 of those dots are unpaired. 3 of those dots are on a side without a buddy, which means that nitrogen has 3 unpaired electrons. So that is definitely the simplest way to be able to find our unpaired electrons. You can use the orbital notation. Sometimes that gives you some different answers though. So don't worry too much about orbital notation for these. I'd really recommend you use the Lewis dot diagram. And remember for nickel, if I wrote out that configuration real quick, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Its valence electrons, the thing telling us how many dots we'd have, are the highest energy level of electrons, 4s2, which means it has 2 valence electrons. So you'll put 2 dots around nickel, and that will help you figure out how many of your electrons are unpaired. So that should finish out the practice on pages 11 through 14. If you don't know which ones go with which, you can ask me in class, but most of them are pretty obviously labeled. But some of these, like 12, 13, and 14, you don't necessarily get told to write a configuration specifically, but they will always help you find that configure if you start with the configuration.